Hi, my name is Noor. Today I'm going to be presenting about the analytical findings and protocol established to determine the concentration of an unknown solution using a virtual UV-VIS spectrophotometer. This method is essential for verifying concentration accurately across standard chemical industrial systems. The primary objective of this investigation is to accurately determine unknown solution concentrations using a virtual platform. This is achieved by verifying internal instrument components, by locating the maximum absorption wavelength, we evaluate the standard calibration compliance, and resolving unknown target values. The
The
basic
basic
framework
framework
is
is
governed
governed by the
by
Beer-Lambert
Beer-Lambert
law,
law,
where
where
absorbance
absorbance
equals
equals
epsilon times
epsilon
length
times
times
length times concentration.
concentration.
Since
Since
path
path
length
length
and molar
and molar
absorptivity
absorptivity
remains
remains
constant
constant
under
under
fixed
fixed
environments,
environmental
a direct
configurations,
linear
a
relationships allow
direct
the
linear
interpolations of
relationship
unknown
allow the
concentration
interpolation
from
of
known
unknown
standard solution
concentrations.
from known standard solutions. So, how this spectrophotometer works? First, we have the light emits from the source. Next, the light passes through the grating, which acts like a filter to choose our exact operating wavelength. Then, that light shines directly through our chemical solution in the sample holder, where some of the light is absorbed. And finally, whatever light gets through hits detector, which turns it into the absorbance reading displayed on our screen. Moving on to the procedure, the experimental steps follow a few sequence. First, we have the spectrophotometer, which is powered on to let the system stabilize. Second, we have a blank cuvette containing pure solvent is placed inside the chamber to zero the instrument, and a standard sample is scanned across 610 nanometers to locate our peak absorbance point. And finally, we measure the absorbance value for our five standard calibration solutions, and then we process our three unknown samples. These steps are repeated with 620 nanometers and then 630 nanometers. This slide compiles our experimental results directly from the software. If we look closely at the standard 5, the absorbance reading grows from 1.102 at 610 nanometers up to 1.212 at 620 nanometers. And we tops out at 1.248 when we hit the 630 nanometers. This clear peak confirms that 630 nanometers is our absolute maximum absorption wavelength or lambda max. And we also notice that while the instrument reads a different absorbance at each wavelength, our final adjusted concentration values stays perfectly consistent throughout the 310 nanometers, 320 nanometers, and 630 nanometers. To analyze the data, absorbance was plotted against concentration to generate these linear regression profiles. Every single run produced an R-squared value of exactly 1.000. That demonstrates a perfect linear compliance with the Beer-Lambert model. The slope or the M parameter also steadily increases with wavelength, moving from 2.208 up to 2.498. This maximum slope of 2.498 at 630 nanometers represents the point of peak analytical sensitivity. To find the concentration of our unknown chemical samples, the linear equations were rearranged to isolate the variable x. Taking our lambda max model at 630 nanometers as an example, You can see that when we plug in the sample absorbance value of 0.450, 0.875, and 1.199, they resolve cleanly to 0.180, 0.350, and 0.480 moles per liter of concentration. Running this same calculation using our 610 nanometers and 620 nanometers lines produces the exact same results of concentration. Does this validate the mathematical work? Moving on to the discussion of analysis. The first question: does the calibration curve obey the Beer-Lambert law? Yes, the calibration curves strictly obey the Beer-Lambert law. This is mathematically proven by the regression plot, which shows a perfect R-squared value of 1.000 across all three tested wavelengths. This confirms that optical absorbance scales in direct linear proportionality with the solution concentration within the tested range. Second question: why is lambda max so important in spectrophotometry? Well, operating at the maximum absorption wavelength gives the steepest calibration slope. If you can look at the graph from 1 to 3, the third graph is like the steepest, which is at the 630 nanometers. This maximizes the measurement sensitivity, meaning that tiny changes in concentration create large clear signals. It also protects the data from minor instrument drifts because the peak is a flat plateau where the reading stays highly stable. For question 3, comparing the scan wavelength shows that as the configuration moves from 610 to 630 nanometers, the calibration slope rises from 2.2080 to 2.4980, proving that 630 nanometers is the peak. And crucially, while the raw absorbance value changes across the three runs, the final calculated concentrations remain completely identical. For example, unknown sample 1 always resolves to exactly 0.180 moles per liter of concentration, either in 610 nanometers or 620 nanometers or 630 nanometers. This proves that the calibration models scale perfectly. So, what errors could affect the results? In real labs, um, the results can be easily compromised by poor technique. Using a contaminated blank sheaves, the baselines intercept, while prints or bubbles on the cuvette walls scatter the light path to give falsely high absorbance readings. And additionally, leaving the chamber lid open lets ambient room light flood the internal detector, which completely destabilizes the reading. Finally, what happens if the concentration is too high? If the solution concentration is too high, the system experiences negative deviation and the calibration curve flattens out. Physically, this happens because closely packed solid molecules undergo near-field electrostatic interactions that distort their charge and change how they absorb the light. The solution also alters the overall effective index of the liquid, which breaks down the linear rules required by the Beer-Lambert law. In conclusion, all core objectives of this investigation were successfully completed. The optimum operating wavelength was isolated at 630 nanometers, displaying an ideal linear adherence. Using the validated regression models, the final concentration of unknown 1, 2, and 3 were confidently determined to be 0.180, 0.350, and 0.480 moles per liter. So that's all for me. Thank you for your time.